Hello, my name is Amkhalang Bukhatsu. I'm here with my team, Butilo Maisela, Umpemeti Luhuzo, Sisonke Kezani, Tesha Mashilo, and Khaledzang Letwana. This video will be discussing one of the many methods that I use to ensure that your drinking water is ready for consumption. We will be discussing an article titled Nanofiltration Membrane Based on Hyperbranched Polyethylamine Functionalized Multi-Walled Carbon Nanotubes for Lead-2 Removal from Water. Many, if not all of the products that you use in your everyday life require the use of very harmful chemicals and heavy metals in their production. The industrial discharge from factories and power plants that are used in the production of these products release these harmful chemicals and heavy metals into water bodies. This essentially results in the pollution of the water that you drink. The presence of these harmful substances in your drinking water will have adverse effects on your health and also the environment. One of these heavy metals presents itself as lead-2 in water. Lead-2 is especially harmful because it results in damage to your cognitive nervous system and your peripheral nervous system. These two are integral to providing a quality of life to you, because they are responsible for functions such as ambulatory functions, motor functions, and even something as simple as standing up straight. The study has therefore identified that we need to devise a method for the removal of lead-2 from water, taking into account its solubility under different conditions. We must ensure that the amount of lead that is in your water meets the standard set. The method that has been proposed for the effective removal of lead from water is membrane technology. Now, membranes are used to facilitate the transport or rejection of substances between mediums and the mechanical separation of gas to liquid streams. Essentially, it serves as a barrier between your wastewater and your clean water. This side, you have your harmful substances, and your membrane will trap them this side so that what you get is the water that you consume every day. To suit the removal of lead-2, the study proposes the use of multi-walled carbon nanotubes in tandem with your membrane as nano-additives in polymer-based composites.
Alright, so we've seen the problem. The author's mission, their single overarching goal, was to build a solution. Their aim is to develop a high-performance nanofiltration membrane with one primary job: to efficiently and reliably remove toxic lead-2 from water. Everything that follows was designed to achieve this specific target. To achieve that goal, the research was built on two foundational phases. First, they had to create the key ingredient. Their first objective was to functionalize multi-walled carbon nanotubes with HPEI. Why these two? Think of it as a perfect partnership. The multi-walled carbon nanotubes provide the structural backbone, like a scaffold offering a huge surface area. The HPE is the active player. Its countless amine groups are what actually grabs and hold onto the lead ions. Combining them created a powerful nanocomposite. The next step was to fabricate the complete membrane. They did this using a clever technique called interfacial polymerization. They took a standard polysulfone support membrane and reacted their new nanocomposite with another chemical called TMC. This reaction forms an ultra-thin selective polyamide layer right on the surface, the true heart of the filter. Once the membrane was built, the authors moved to the crucial phases of analysis and testing. They needed to answer two questions: did we build it right, and does it work? So first, they characterized the membrane. They used techniques like FTIR to confirm the chemistry, SEM to see their physical structures, and contact angle to measure hydrophilicity. The result here was spectacular. The contact angle plummeted from a very hydrophobic 122 degrees down to 63 degrees. This massive increase in hydrophilicity means water flows through it much more quickly, a huge advantage for a filter. Finally, they evaluated its performance with the only thing that really matters: a test. They checked if its efficiency under different conditions like pH and concentration And the key result says it all. The membrane achieved over 95% removal of PP2 in less than 10 minutes. This isn't just effective, it's incredibly fast, and now my colleagues will take us through exactly how they did this and why this process is so effective.
Alright, I would like us to look at the characterizational techniques used in this experiment. Now, the first one I would like us to look at is the Fourier transform infrared spectroscopy. Now, this is the analysis of the MWCNTs, which are multi-walled carbon nanotubes. Now, how were they analyzed? Now, the samples were crushed into fine particles and mixed with the potassium bromide. Then after that, the sample was taken and the Fourier technique was used to analyze the sample where the active side was facing the machinery, and then after that, the functionalization of these multi-walled carbon nanotubes was analyzed. Now, the next method I would like us to look at is the Brunner-Emmett-Teller technique. Now, this is the determination of the specific surface area of functionalized MWCNTs, as well as their pore volumes and pore sizes. Alright, the next method we will look at is the transmission electron microscope. Now, this is the analysis of the shape, quality, and size of the MWCNTs. This is done by passing an electron beam through a sample to produce an image. The next method is scanning electron microscope. Now, this method was used to study the surface morphology of the membrane. How this was done was that the membrane was placed in a sample holder and coated with a thin carbon film and then analyzed with a Tascan electron microscope. The next method is inductively coupled plasma optical emission spectroscopy. Now, in this method, the lead in the working solution was determined. Now, how this was determined was that the working solution was placed in an inductively coupled plasma optical emission spectrometer injection device before and after adsorption.
Patch absorption. A lead stock solution of 1000 milligrams was diluted with deionized water to prepare a series of solutions with concentrations of 5 to 50 milligrams per liter. For each solution, 50 milliliters was placed in a 250 LMA flask. A 4 centimeter squared piece of absorbent was added. The pH was adjusted to 5. Mixture was agitated at 124 RPM for 30 minutes at room temperature using a mechanical shaker. 10 milliliter samples were taken at 10-minute intervals. PB concentration was analyzed using ICP-OES, Thermo Fisher Scientific. The percentage of lead removed is calculated using this equation, and the absorbent capacity was calculated using this equation. Results and discussion. TME and size distribution analysis of pristine and functionalized MWCNTs. Pristine and functionalized MWCNTs, which is multi-walled carbon nanotubes, maintain their tubular structure. Functionalization slightly reduced diameter by grafting hyperbranched polyethylamine, increasing the diameter due to polymer coating forming a core shell structure. Characterization of HPI MWCNTs, analysis of membrane, confirmed the successful interfacial polymerization of HPI MWCNTs onto PSF membranes. This was evidenced by disappearance of acyl chloride peak at 1,758 centimeters and the appearance of new amide peaks, indicating a reaction between HPEI and TMC, which is trimethylchlorosilane. These findings are consistent with previous studies, confirming the effective incorporation of HPEA into PSF matrix. Scanning electron microscope analysis showed that unmodified PSF membranes had smooth surfaces, while membranes with HPEI and MWCNTs became rougher as nanocomposite loading increased. This change in surface texture confirms successful interfacial polymerization and formation of a new polyamide layer.
First, in the batch absorption studies, we found that lead-2 was highest at pH 6 and pH 2 with optimum pH selected as 6. Above pH 7, adsorption decreased because of reduced protonation and precipitation of lead. In terms of efficiency, at pH 2, removal was around 66% for pristine material and slightly higher for composite. At pH 6, removal went up to 98% for 0.1% and 1% composite. The adsorption mechanism is mainly in electrostatic interaction between lead ions and protonated amine groups. Kinetic studies showed that the pseudo-second model fit best, meaning chelating and electrostatic interaction dominate, with diffusion as the rate-limiting step. For adsorption isotherms, the Langmuir model fit better than the Freundlich model. Maximum capacity with higher composite content reaching 0.51 mg per gram for the 1% composite, showing strong affinity for lead. Lastly, interference studies confirmed that the composite, especially the 0.5% one, had high selectivity for lead over other metals.
The interference study was carried out at the pH of 6 with a 40-minute contact time and a metal ion with a concentration of 10 milligrams per liter. Under these conditions, the hyperbranched polyethylenamine HPEI, multi-walled carbon nanotube MWCNT, and the PSF polysulfone of 0.5% membrane showed very strong selectivity for lead ions. The results revealed that the membrane removed 99% of lead-2, 96% of zinc-2, and 95% of copper-2. In contrast, cadmium and nickel were barely adsorbed. This demonstrates that lead-2 has the highest affinity, followed by zinc and copper. The high selectivity for lead-2 is explained by the covalent bonding between the lead-2 and the cation and the nitrogen atoms of HPEI, supported by the ion exchange and electrostatic interactions. According to the hard and soft acid and bases HSAB theory, cadmium is a soft acid and nickel is a borderline acid, and it interacts weakly, while the lead-2, Z2, and copper-2, being borderline bases, bind more effectively. Overall, the affinity order was lead-2, zinc-2, and copper-2. This confirms that the membrane is highly efficient for lead-2 removal, while still capable of simultaneously adsorbing zinc-2 and copper-2, making it practical for real water treatment. The study successfully incorporated HPEI MWCNT onto PSF membrane using interfacial polymerization, confirmed by the Fourier transform infrared spectroscopy, the FTIR, and the scanning electron microscopy, the SEM analysis, which showed a polyamine film formation and a morphological changes. This work was supported by the Tutuka National Research Foundation, NRF, Water Research Commission South Africa, ESCOM, TESP, DST, Mintech, and the Center for Nanomaterial Sciences Research, CSNR. The work that was presented in this video was researched and compiled by Edward Rorisang Masinye, Prof. Nomhlangabezo Mabuba, and Soraya Phumzile Malinga.